in case you have fallen asleep by then. So Fokion's lecture on repairing damaged databases remind me of a joke Dave McQueen told me many years ago. So there's this robot that has been built as a prototype to perform household tasks, and it can actually understand natural language. So you can speak to it in ordinary English. And it has this repair mechanism built into it so that it automatically corrects mistakes in things that it hears. So they field test it by sending it to a neighborhood, and it's supposed to go from door to door and offer to do household tasks. So it goes to a house and it says, is there anything you want me to do? And the guy says, yeah, go paint the porch out back. So the robot goes with a can of white paint and comes back after an hour and says, I have finished. By the way, it was a BMW. So these are amongst the dangers of automatic repair mechanisms. So last time, or yesterday, it seems like years ago, but it was just yesterday, I talked about bisimulation as a way of talking about behavioral equivalence of systems or states within a system. And I argued that it was not such a good thing, in fact, to rely on something as brutally abrupt as a yes-no concept like an equivalence relation when you have quantitative data describing your system. So today I'm going to talk about metrics, which give you a more graceful and more quantitative way of relating system behaviors. Okay, so I will, after a brief introduction, I will talk about metrics for bisimulation, and then give a kind of logical view, this time based on a real valued modal logic. And finally, I will conclude with concluding remarks. So process equivalence is fundamental, as we have seen before with Markov chains. In fact, the concept, a concept very much like bisimulation, was already there in queuing theory as far back as the early 60s. It was called lumpability, and the name is very evocative. It means you can lump those things together if you discover that they satisfy this particular behavioral equivalence relation. For labeled Markov processes, as I described yesterday, we have this concept called bisimulation. And indeed, later on, we extended this to Markov decision processes, where you have a notion of reward. You also have a bisimulation concept. Independently, and a few years later, this was rediscovered by people in the machine learning community. One can also look at so-called labeled concurrent Markov chains, where you combine probability and non-determinism. So you have a notion called weak bisimulation, and you really have to start struggling with the difference between probability and non-determinism and their interaction. But for all these things, you have equivalence relations that capture some kind of behavioral property of interest. But in the context of probability, this kind of exact equivalence relation is not very reasonable. A small change in the probability distribution leads to suddenly saying, oh, suddenly things that had been bisimilar are no longer bisimilar. And yet they might be very close in their behavior, and we would like to capture this in some quantitative way. So the idea is that one should have a pseudometric for probabilistic processes. So let me just remind you what a pseudometric is. So it's just like a metric. It's a binary function on some space that gives you positive real numbers that you should think of as being like distances. And importantly, if you have the distance from a point to itself is 0, but you can have distinct points at 0 distance. That's why it's a pseudometric rather than a regular metric. Now, there are other variations that have also been considered, like hemimetrics, which are not even symmetric, something that has been brought home to me as I cycle to work and back, up and down the hill. But in general, in geometry, one likes to consider symmetry as a defining property of pseudometrics. And one has the standard triangle inequality. Now, the point is that this is a very nice analog, quantitative analog of the notion of equivalence relation. You can think of this thing as saying everything is close to itself. You can think of this thing as saying if something is close to something else, then the reverse also holds. And this one is like a transitivity thing. If S is close to T and T is close to U, then S will be close to U. Okay, so in some quantitative sense, this is very much analogous to the notion of an equivalence relation. So it seems to be the natural replacement for that. If you insist that X and Y can be at zero distance if and only if they are the same, then we get the standard notion of metric. And if you have such a pseudo-metric, which doesn't impose that, then you automatically get an equivalence relation by deeming 2 points to be equivalent if they are at zero distance. You can then, of course, quotient by that equivalence relation to get a bona fide metric on the appropriate equivalence classes. And this is well defined by the triangle inequality. Okay, so that's a brief summary of metrics and pseudometrics. These are going to be the things that I will be using to compare the behaviors of systems. So let's look back at bisimulation. So we had an equivalence relation, and we said that two states S and T were bisimilar if S could jump by an A transition and produce some kind of probability distribution, say P, then T could also jump to some other probability distribution, and P and Q should be somehow R related. I will say exactly what this means, and vice versa. So this notation means basically that P and Q agree on unions of R equivalence classes, so on R closed measurable sets. So this is the definition from yesterday. And now, again, this is an equivalence relation. We'll say S and T are bisimilar if I can find a bisimulation relating them. So basically, if you're trying to prove two systems are bisimilar, you look around for an appropriate R that relates the two that you're interested in. And you can prove the standard things. There is a maximum bisimulation relation, which is bisimilarity itself. Now, the basic properties that you want to mimic in the quantitative case, one is that you have this kind of co-induction principle, namely that if you can find a bisimulation R that relates S and T, that gives you a technique for showing things are bisimilar. This is basically the greatest fixed point property of bisimulation. How do you tell if two states are not bisimilar? Well, you use a logical characterization, and you look for formulas on which they disagree. This will tell you that things can't be bisimilar if you found a formula on which they disagree. The nice thing about this particular modal logic is that you can interpret these modal formulas as experiments that you can do to try and make manifest the difference in the behavior. Okay, so if you see some nested sequences of diamonds, you say do an A and then a B and then a C, and then you will see that something doesn't match up. So it's actually giving you a thing to look for. In fact, there is a famous case study which was done by the Upal group at Aalborg, who implemented a real-time model checking system, which included things that could check for timed bisimulation. And there was this case study which they did in conjunction with Bang and Olufsen, where they had a system that was misbehaving. For about 2 years, the engineers who designed the system couldn't debug it. They knew something was wrong, but they couldn't exactly pin it down. And then the Aalborg group spent about 3 or 4 months developing an abstract model of the system and then running it through their model checker and asking it if these two things were bisimilar, the specification and the description of what had been built. And it said no, and it produced the witnessing formula that showed that they weren't. And that was, in fact, a trace of the behavior where the anomaly showed up. So this happened some time back, but we still repeat it as one of our favorite case studies of where the theory and the practice got together. So being able to distinguish states through such a simple logic is actually a very nice thing. So back in 1990, Joe and Scott Smolka suggested that one should move from an equality between processes to such a pseudometric. Okay, so this gives a quantitative measure of the distinction between processes. They actually proposed a metric, which was quite an interesting one. It had, unfortunately, one bad feature, which was there were things that were at zero distance that weren't bisimilar. So it was, in fact, quite difficult to come up with a metric that had the feature that you wanted, which was, yes, zero distance should correspond to I can't see a difference at all. It should correspond to the equivalence relation of bisimilarity. And that's what we finally did almost a decade after that. So the basic results that one is able to establish in this case is an analogous co-induction principle, an ability to kind of a logic, which is this time a real valued modal logic, which allows you to distinguish states, and a proof that the equational and the logical views actually coincide. So this particular proof was done by Frank van Breugel and James Worrell. One can also imagine applying this not just to label transition systems, but one can imagine a syntax, a primitive programming language, if you will, for describing these systems. And you can show that process combinators take nearby processes to nearby processes. The basic property here is non-expansiveness. If things are at certain distances, then when you combine them, they will still be close. Okay, and this is the analog of being compositional. So these kinds of results we actually did for a variety of closely related systems, Markov chains, MDPs, and so on. Okay, so what do we want? We want, first of all, that if the pseudometric says that two systems or two states are at zero distance, we want them to be properly bisimilar. We would like this distance to stay stable under temporal evolution, so nearby states shouldn't diverge soon. They should stay close for a long time. Otherwise, you have no right to call them similar if they quickly manifest differences. Ideally, the metrics should be computable. And I will say a bit about all these things presently. So let's go back to the definition of bisimulation. Here it is, written out again in the same way as before. And we would like to convert this now to a quantitative definition. So here's something we can try. Let's imagine that we have a metric on the state space. So I'll call it M. And let's suppose that these two states are close. Well, what should that mean? That it should mean that whenever S can do a transition to P, and let's forget about labels for now. So let's assume there's only one label. So S does a transition. It scatters out to some probability distribution P. Then T should also be able to scatter out to some probability distribution Q, and those should be close as well, and vice versa. So this looks like a very close analogy with what we had with the definition of bisimulation, except that this metric was defined between the points of the transition system, and here I'm using it between the distributions defined on top of that same metric space. So this is a type mismatch. It's not the same thing. It's not the same space, of course. So what we need is some way to lift distances from states to distances on distributions over the states. And this is the main technical part. So I'm going to go through a longish detour through the so-called Kantorovich metric. So this metric, as I said before, has many names. It was often called the Hutchinson metric, the Earth mover distance, the Wasserstein metric, the Kantorovich metric, and so on. I think it's fair to attribute it to Kantorovich. So Villani, who has written a 1,000-page book about transport problems, has a long, at the end of one of his chapters, has a long discussion on why it should be called the Kantorovich metric. So this is a metric on the probability measures themselves defined on a metric space. I said before that probability theory works well when you have a metric space. So let me introduce script M to be the lattice of one-bounded pseudometrics. Right now it's just a set. I will give it lattice structure presently. And now the distance, that one natural way of measuring the distance between two distributions is to say, well, how differently do they compute integrals? So you look at non-expansive functions. So you say you integrate one of them with respect to one of the measures, and then with respect to the other measure, and you see how different the answers you get are, and then you look at that sort of maximized or souped over all f in that class. So this is one very nice metric that one can use. And it turns out that this metric actually arises in a linear programming problem called transshipment. So it's actually a classic transportation problem which yields this particular metric, and that's how Kantorovich came up with it. So it's actually interesting to note that Kantorovich published his paper in 1942, which was, of course, in the middle of World War II and shortly after the invasion of the Soviet Union by Germany. And there was a big transportation problem that the Soviets had to deal with, which was to move all their factories and industrial production east. So I'd like to think that this was greatly facilitated by Kantorovich's techniques, but I don't know if that's actually true or whether Stalin actually listened to Kantorovich, but it's nice to imagine that this was one of the things that contributed to the defeat of Nazi Germany.
Prakash, is it clear that this is a finite number, the soup?
Is it clear that this is a finite number? The distance could be infinite, yes. So not on a compact set. If the underlying space is compact, no, it will be a finite number. But in general, it could be. So I should say, in general, we allow metrics that take on extended real number values. Right. If I am permitted to say category on the last day, let me say the category of metric spaces with extended metrics is a much nicer category than the usual one. But
after all, it's comparing categories, so who cares?
You remind me of Linda Ronstadt, who said categories are out. Okay, so Thomas?
It's obvious why one Lipschitz is something to be put there.
Yeah, is it obvious? Well, you need some kind of condition, because otherwise, if I allow you to have absolutely wild functions, I can pick things that really focus on where they differ, and then you don't have any control over the behavior of the thing. Yeah.
Prakash,
Yes?
does this metric amount to a lifting of the probability distribution monad to some category of metric spaces?
Yes. I think that's right. Not exactly like this, but yeah. So Frank has written a paper called the metric probability monad, which I think, it uses the Kantorovich metric. But I have not explained this transshipment thing. So let me do that by talking about it in a very discrete setting. Are you happy, Thomas, or are you still want some compelling argument?
For after, I find a joke with category. Well, reasonable.
Yeah, okay. So let's look at finite state spaces. All right. So we've got probability distributions on a finite set, and the set is the underlying space is given a metric structure. So I can sensibly talk about the distance from a point Si to another point Sj. So there are n points or whatever, S1 through Sn. And now the role of those f's is played just by these numbers a sub I, which are required to be between 0 and 1, let's say. And this condition is the discrete analog of being Lipschitz, so non-expansive. And now that soup has become a max, and what it says is try and choose these AIs subject to these constraints to maximize this, and that will define a metric on the distributions P and Q. Okay? Doesn't yet, it's just a discrete analog of the thing I wrote down before in terms of integrals. It doesn't yet look like it has anything to do with transshipment. So the dual form, which I learned from a paper of James Worrell and Van Bruegel, looks like this. So instead of maximizing something, you minimize this expression where now the variables are these Lij's. Ignore the xi's and the yj's for now, or in fact forever. They are what are called slack variables for certain, which are put there for certain convenience. But these are really the things to focus on. Now, what the heck does all this mean? So maybe I will switch to the board to explain what's going on. So here is one intuitively compelling way, I think, to compare two probability distributions on a metric space. So let's say, oops, should have the same number of points. Yeah. So let's say I have a copy of the space, and at each point I have put some pile of stuff. So a pile of sand at each point. And then, so that of course I can think of as the shape of some distribution over the set. And I want to move it to something shaped differently. Okay. So in order to do so, I have to ship sand around. Perhaps this place needs to have more. This has a lot of sand on it, so I can move some from here to there. So you see, I transport some sand from here to there. So if this is I and that's j, how much I ship from point I to point j is the Lij appearing in that. Okay. Now, of course, associated with shipping a certain amount of sand from one place to the other is a cost, and the metric is measuring that cost. So what the Lij defines is called a transport plan. And this thing is measuring the cost of that plan. So what we're asking you to do is find the minimum cost transport plan to transform one distribution to another. And this turns out to be actually dual to the previous maximization problem. Okay, so this is a very manifestly a shipment problem. And this is a transshipment.
What about the sums of the xi's and the yj's?
Yeah, so these are what are called slack variables to take up discrepancies. If P and Q are sub-probability distributions, you might want to have these so-called slack variables to take up the difference. But if, in general, these things will always end up being zero, at least in the examples I look at. Okay, so putting them there allows me to actually deal with sub-distributions that don't even have the same total mass.
So you could put inequalities and get rid of them. Is that what you're saying? In the constraints.
Yes, you mean I could have made them inequational constraints? Yeah, I could have, but this is a nicer way to do it. Okay, so what's nice about duality is, when you first teach duality to students, they might say, oh, you've replaced one problem with another. One's a maximization, the other is a minimization. But the point is, one form allows you to prove upper bounds on things, the other one allows you to prove lower bounds, and with the two of them together, you're able to squeeze things and prove equations. This is what we had to do a lot in this work, prove various equations by exploiting both aspects of the dual formulation. So let me do some examples. Again, very, very simple examples, because that's all I think I can handle right now. So let's show that the distance from a distribution to itself is indeed zero. Okay, so you match each state with itself. So the transport plan is don't move anything. All right. Well, that's it's easy to figure out the cost of that plan. It's zero. And and now this clearly cannot be lowered any further, because this version says minimize the cost. We've already got down to zero, so this must be the minimum cost plan to ship a distribution to itself by simply not moving anything. So this is a very quick and immediate proof that this lifted metric has distance zero. Not so easy to prove in the other form. Okay, supposing I have 2 points, and let's say the distance is strictly less than 1. And now let's look at the Dirac distribution totally concentrated at the point S and compare it with the distribution concentrated at the point P. The point T. So this lifted metric, you see I'm using the same letter M because I want to, this example will kind of justify it. I want to show that the distance between the distributions is also R. And now what you can do is simply say, well, everything was at S. I want to move it to T. It's kind of obvious what the transport plan is. Ship everything from S to T. And then there's nothing else that needs to be shipped. And the cost will indeed turn out to be R. But now this is only giving you an upper bound. to get the lower bound, you have to look at the other form, and now you can choose AS to be 0, AT to be R, and all others to match the constraints, and then you can get that sum is R. Since we've matched the lower bound, you actually know that you now have an equality, and this distance is R. So why is this important? It shows that the original space isometrically embeds inside the space of distributions. Okay, so it kind of justifies the sloppiness of writing M for both kinds of things, because it just lives there in terms of its Dirac distributions. So the third one is supposing the probability of S is R and T is 0. And now I move it to S having R prime and T also 0 for all other things other than S. Now what I've done is I've lost some mass. So that now I'd like to claim that the distance between the distribution is just the absolute value of the distance between R and R prime. Okay, so again, you can just choose appropriate choices for A from the primal, and you can choose transport plan for the dual. This time you'll need a non-trivial X, because you see I don't have full distributions. And then you can check that the constraints are satisfied, and indeed you get this distance. Again, because you've got it from both of them, you know that you've achieved the right distance. Okay, so this detour, again, I did it for really simple examples. But the summary is that given a metric on states in a metric space, given a metric on the states, you have a metric space, you can lift this to give a metric on the probability distribution on states. And indeed, as Bartek pointed out, you actually get a nice monad on the category of metric spaces. But you probably didn't want to hear that. So now we can do metric bisimulation without the type anomaly that I had before. So we basically say this is the idea. If I have two things that are close in my behavioral metric, so less than some distance epsilon, then after making transitions, they should be close. That's just the quantitative analog of what I had before when I had strict equalities. Now I just say they should be close. So the required canonical metric is the least such thing that satisfies this condition, so i.e. the one in which the distances are the least possible. So what actually happens is that you can actually prove such a metric exists by the following argument. So let me just remind you of Torquay's theorem, which has proved to be a unifying thread in 2 or 3 different series. So if you have a complete lattice, which I have managed to misspell, and you have a monotone function from the lattice to itself, then the set of fixed points of F with the induced order is itself a complete lattice. In particular, there is both a least fixed point and a greatest fixed point. Of course, they may coincide. But in general, you'll get a nice lattice of fixed points. Okay, so here is how we use it here. So recall that we had this script M, a family of one-bounded pseudometrics on states with ordering. So I'm going to define this order, which is kind of the reverse of the distance ordering. So if M1 assigns bigger distances than M2, then I will say M1 is below M2. This may sound a bit peculiar, but there's a fairly good reason for it. It's completely routine to check that this is a complete lattice. And let's look at what the top and bottom look like. So this one says S and T, bottom says S and T are 0 distance if S is equal to T, and otherwise it's the maximum possible distance. Remember, these are one-bounded. So the top one simply says everything is at 0 distance. Since these are pseudometrics, I can say stuff like that. And this is written this way with this ordering, which you might think is reversed from its natural order, because it more closely resembles the lattice of relations. Because if you look at the lattice of relations ordered by inclusion, then the bottom element would indeed be the guy that doesn't relate anything except everything to itself. Let's say the lattice of equivalence relations. And the maximal element would be the one that says everything is related, which is indeed, if that was my pseudometric, the induced equivalence relation would indeed relate everything. So in fact, this reversed ordering is indeed the one that corresponds to how we were thinking about relations before. So now I will define a functional on this lattice which says f of m between s and t is close if after a transition the distributions p and q that you get are close. So f gives you kind of a one-step unwinding of the transition relation. And because this is a probabilistic transition system, after a transition, instead of a state, I have a distribution, but that's okay now because my metric actually measures distributions as well as points. Okay, so you can actually write down an explicit expression for this rather than this more suggestive form. So you can show that f is monotone, and metric by simulation indeed is the greatest fixed point, can be defined then as the greatest fixed point of this functional on the lattice of pseudometrics.
Sorry, that's a definition.
Sorry?
That's a definition, not a. You said you can show. So
No, you can. I think I quickly corrected show to define. If not, I'm doing it now. So you can show f is monotone and hence define metric by simulation to be the greatest fixed point. Okay, so I don't want to tell you anything about these proofs except to mention a key tool which also appeared in Mike Mislov's talk on Tuesday, called the splitting lemma. So this splitting lemma is not exactly the one Claire Jones came up with, but it's closely related and was proved by my student Jose. So it says if you have two probability distributions on a set of states and you split P into a pair P1 plus P2, so these will be in fact subprobabilities, then you can also split Q into Q1 and Q2 such that the distance from P to Q will be the sum of those two things. So you can actually, this will allow you to take two distributions and split them up into simpler pieces and piece together the metric distance from the individual pieces that you've constructed. So this turns out to be a very crucial tool in almost everything that we prove. And you use this in the discrete case just by ordinary LP theory, linear programming. But on continuous spaces, you need a more powerful theorem called Kantorovich-Rubinstein duality. So I will tell you what that is now. So it's just the analog of this thing, except you don't have points, but you have some kind of metric spaces. Okay, so let me define the terms here. Supposing I have two probability measures on some measurable space, what we call a coupling is a measure on the product space, such that the marginals are the two measures that you started with. Okay, so you have two measures, you think of them like this. So I have the product space x cross x. The distribution P1 is the marginal along the x-axis. The distribution P2 is the marginal along the y-axis, and you build some kind of joint measure on the product space such that you match the marginals. So when you do that, that thing that you get is called a coupling. Okay, so I'll write C P1, P2 for the set of all couplings between P1 and P2. And you can think of this as just generalizing that idea. It's giving you a transport plan for shipping stuff around from one place to the other so that the distribution P1 is transformed until it becomes P2. Okay, so P1 might have some shape, P2 will have some completely different shape, and you have to move things around until the shape P1 is transformed into the shape P2. Pi is telling you a particular plan for doing that. Okay, there are, of course, many different plans. Any such plan will be one of those couplings. So the theorem says, if I have a metric on the underlying space that's measuring my cost, and I integrate, so if Q is one of my couplings, so that means if Q is a transport plan for transforming P1 into P2, then the cost of that plan is this. And now I take the inf over all possible couplings. This is equal to the sup, again for f non-expansive, of this difference. Okay, so again, this one is measuring how differently P1 and P2 evaluate integrals, and this one is measuring how much it takes to transform one distribution into another. And the Kantorovich-Rubinstein theorem says basically these will be the same. Okay, so there are various assumptions that for example, that the thing has to be compact. But these have been, over the years, weakened so that the conditions have been weakened, that is, so the theorem has been strengthened. And
you don't want absolute values in the first one?
Well, I probably do, sorry. Yes.
Just for intuition, can you say what transport plan the product measure corresponds to? So the standard product measure of...
No, not the product measure. A measure on the product space.
Yeah, I'm just...
What plan does the product measure correspond to?
Just so that we have some intuition how the discrete worlds look.
Plan that takes all the stuff in P1, throws it into a big bag of random, and then randomly redistributes it to P2. So that where you end up is independent of where you began.
You mean if you do P cross P?
Yeah, so each person sort of distributes their own bag of sand according to the end distribution along the...
Yeah, I'm not sure who each person is, but...
yeah, okay. That would be that.
So there were many variations on this. The original formulation as given by Monge was about transporting rocks. So what the difference between rocks and sand is because you can't break up rocks. Sand is infinitely divisible and you can redistribute it as much as you like. The Monge version said, I have a bunch of rocks here with this total mass at each place, and I want to move it to another bunch of rocks there, and that may or may not be possible. So it turned out to be a much harder problem, and Kantorovich said, let's smash these rocks and make them into sand, and then you can actually do it efficiently. You can efficiently come up with a plan. Okay.
It is called sometimes Monge problem.
Sorry?
It is called sometimes Monge problem.
Yes. Oh, yeah. So, but the difference between the Monge problem and the Kantorovich problem is precisely this business about being divisible. Yeah. So I like to think of it as rocks versus sand. It's sometimes called the Monge-Kantorovich problem, and sometimes it's called the earth movers problem. But I've never heard it being called the rock movers problem. So this particular metric coming out of Kantorovich duality is also very much used in computer vision. They're the people who started calling it the earth movers distance. And they use it to compare. So they think of an image as just a probability distribution of pixel intensities. And they use it as a comparison between two images. Okay, so that was imitating the bisimulation point of view. So let's look at a more logical point of view. So I want to develop a real valued modal logic.
Can I ask you a question?
Yes, absolutely.
The definition of the simulation in this sense, in the metric sense, you insisted that the epsilon was the same.
Yeah, that
Does it make a difference?
doesn't make a difference. That was kind of a semi-formal definition. The actual f, there's an actual functional you can write down explicitly, and that's the thing whose greatest fixed point you compute. Yeah, I just wrote it like that so that I could say things that are close stay close. I could have called it epsilon and epsilon prime, but then you would have asked what's the relationship between epsilon and epsilon prime. So the logical point of view. So we want a real valued modal logic based on this analogy which I learned from Dexter-Cozen. So normally you think of program logics like this. You have a set of states, you have formulas, and you have a satisfaction relation linking them. And in the probabilistic world, instead of states, you have distributions. The analog of formulas are random variables, and the analog of satisfaction, the link that hooks these two together, is the integral. So indeed, this particular analogy can I like to call it the hinge of duality. So there's a stone type duality here. There's a very analogous duality between, which I alluded to, I think, on Wednesday. So anyway, this is the kind of thing that led us to think about a metric based on how closely random variables agree. Okay, so this is an alternative to the Kantorovich metric point of view. So let's define this kind of syntax. So we have, so this is just notation for what I'd like to call functional expressions, if you wish. Right? Syntax for functions. I have to give you a semantics for how to interpret this syntax on a given Markov process. So there's the constant 1, max of 2 functions. I can compose f with h. I'll tell you in a minute what h is. And then there's this funny diamond a dot f thing, where a is one of the actions of my transition system. So h is any Lipschitz functions from the reals to the reals. So I'm allowed to compose that with my function from the states to the reals. So that's just functional composition. Max is max, 1 is 1. And now this a. So a dot f is a new function. And the way you describe it is you take the transition kernel I talked about at length yesterday, and you integrate f with respect to that. So you're computing the expectation value of f after an a transition has happened. Okay? Right. Now, it turns out convenient to put in a contractive factor gamma, which might, in fact, not be contractive because I've put the closed interval 1 here. And indeed, whether gamma is 1 or not will make a stark difference. Okay, so that's how you interpret these functions. And now we can define a metric by saying, take the soup over all the functions that we get from this syntactic description. So it's not exactly so syntactic because, of course, I'm allowing you to then compose with an arbitrary Lipschitz function, but I will actually make it more finitary presently. You take the soup over all such f's of the difference between f of s and f of t. So you can see this was kind of inspired by Kantorovich, Kantorovich-like distance. And it turns out you can prove that well, first of all, that this is indeed a proper metric, but that metric coincides with the fixed point definition of metric by simulation I gave before. Okay, so this theorem is actually nothing but the quantitative analog of the logical characterization of bisimulation result that I talked about yesterday.
The theorem doesn't depend on the choice of gamma?
That theorem does not depend on the choice of gamma. That's correct. However, other things do depend on the choice of gamma. So, in fact, there's a good, well, I will talk about gamma and its role a bit later. A more finitary syntax for these functions is as follows. So we allow this kind of negation by allowing you to write 1 minus f. In addition to the diamond a dot f, we introduce this new thing called a cutoff. So what this cutoff does is it says we will, if f of s is greater than q, we will cut you down to q, otherwise we will let you be. Okay? And here again we insist on q being a rational. So now you have a finitary syntax for this modal logic, and you can actually prove that you get exactly the same metric as the syntax that I had before that allowed arbitrary Lipschitz functions to be composed with your f's. Okay, so this is now the logical view of the same distance. Okay, the role of gamma. So what the heck does gamma do? So what it does is it discounts the value of future steps. So it's saying if you're trying to compare two processes that are evolving dynamically, then if their difference appears after a long time, you'll discount that and say, yes, they're very similar. After a long time, they might start looking different, but since it took so long, we will discount that and not count it as much as if they manifested differences immediately. Okay. This kind of discounted distance or discounted value functions and so on appears all over machine learning, all over MDP theory and stuff like that. But what happens if gamma is 1? If you look at the topology that you get, gamma strictly less than 1 and gamma equal to 1 yield very different topologies. And perhaps it's worth showing examples that illustrate this. consider this sequence of systems. Right. So, and compare them to the system that just cycles on itself. So if gamma is strictly less than 1, these things actually converge to that one, because the time when you see the difference gets postponed further and further. So if gamma is equal to 1, these things are always at the same distance from that self-looping thing, and they will never converge. So it's not just that they yield different metrics, they actually yield different topologies. So if gamma is strictly less than 1, it doesn't matter what the value is, you will always get the same topology. If gamma is equal to 1, you get a very different topology. It also makes a big difference for decision procedures. For gamma strictly less than 1, there is an LP-based algorithm to compute the metric. This was also one of the contributions of Frank van Breugel and James Worrell. But it's kind of clear that if you specify, so what does it mean to say you have a decision procedure for the metric? I tell you a certain epsilon and I say, please tell me the metric to within that epsilon, right? So you specify an accuracy. Well, if you know what the discount is, then you can estimate how far you have to go to compute that, to that level of accuracy. So it's not difficult to imagine algorithms to do this. In the case when gamma is equal to 1, we were not sure for a long time whether it was even decidable or computable. And eventually, Van Breugel, his student Babita Sharma, and Ben Worrell came up with an algorithm to compute this metric. It uses Canny's result on existential theory of the real closed fields in p-space. So I think it's a p-space algorithm. Now, the whole point of using metrics as opposed to exact concepts like bisimulation was because one wanted to do approximate reasoning. So underlying this whole subject was a lot of work on approximation of labeled Markov processes and of the metric that describes these things. And that's what we've been doing for quite a long time now. So one of our early approximation results was even when you have one of these big uncountable state spaces, continuum, you can still find a sequence of finite state approximants to any LMP such that the following things hold. That sequence converges in this kind of metric to the original LMP. So that's very nice. In fact, you can say more. So remember that an LMP is described by the formulas it satisfies. You want to know whether a particular formula holds of an LMP. You can actually prove that any formula that's satisfied by the LMP will be satisfied at some stage by one of the finite approximants. And later on, José Desharnais and Vincent Danos proved related results. They said, okay, if you're interested in just this family of formulas and not generically knowing what formulas an LMP satisfies, we can tell you how far to approximate it so that you'll get definite answers to the formulas in that restricted class. So that was kind of nice. You can actually orient your approximation process and skew it towards answering specific defined class of queries. Okay, so it converges in the metric to the original LMP. Now, one thing I didn't talk about at all in my lectures is domain structure. It turns out you can actually make the collection of labeled Markov processes into a continuous domain. So there are, well, obviously there are no compact elements, but it's still got a base of things that you can think of as finite elements. It's in fact omega continuous, and you can show that these approximants that we constructed actually form a directed set, in fact a chain, and converge in order as well. Okay, so the order convergence and the metric convergence actually coincide. Both give you a notion of approximation of labeled Markov processes. And in fact, by solving an appropriate recursive domain equation, you can construct a universal LMP, a final coalgebra if you wish, if you wish to use that language. But roughly speaking, what it means is that any LMP can be embedded inside this universal one. Yeah?
Does this work for any metric space, or do you need something nice like Polish or analytic?
You need quite a number of nice things.
Okay.
So the domain theory thing has analogous domain theoretic things. It's got to be Lawson compact something domains, but definitely not. Definitely not any old spaces.
Sorry, can you say again what a universal LMP means? That you can embed every labeled Markov process of any uncountable blah blah blah. You can embed inside this thing.
Yeah. But of course, it's in that category. So if I'm building a universal LMP on top of Polish spaces, then it'll be any LMP on any Polish space will be embedded in this one.
Okay, you can't jump levels.
No. Or we did it. So the purely metric one was done by Frank and Ben, but the domain one, so any one defined on one of those domains, which were basically Lawson compact domains, you can you can embed any LMP defined on such a thing inside this universal one.
What are these things good for? Like, what do I do with a universal thing like that? Sorry.
Show it off on your mantelpiece, but you can well. So the distance between processes are actually exactly the distance that their images are in the universal one.
So you built it in some like a Fraser image and completion?
Yes, you did. You build an inductive construction, exactly. The same way that one normally solves recursive domain equations. Okay, so one can also do all this with MDPs, which is where you have rewards as well as all the other parameters that one has in Markov processes. And now you can do some quite interesting things with this. You can give bounds on approximations to the optimal value functions, and all the papers we wrote on these things tend to appear in AI conferences or machine learning conferences rather than in the logic conferences. But an example of the kind of thing you can do is the following. So let's say you learn a certain policy for an MDP on some example, and then you say, okay, I'm going to try and transfer what I've learned to some other MDP, not the one on which I learned it. And how good would that be? Right? So it was optimal for this one. How good would it be for the other one on which I'm going to use it? Perhaps you trained it on a small example and you want to use it on a big example. Well, unlikely to be optimal. But it turns out you can bound how far it is from optimal in terms of the metric between the two LMPs. So it gives you some control on how things like value functions behave. So this you might think is a great thing. Unfortunately, you can also try to use metrics to give you clustering techniques for collapsing bigger MDPs down to much smaller ones. Unfortunately, computing the MDP is much more expensive. Computing the metric is more expensive than computing the value function in the first place. So this motivates algorithms to approximate the computation of the metric. And there are a number of papers, some based on, instead of trying to compute everything exactly as we did in the purely theoretical work, but using sampling or using some kind of asynchronous update. You don't have to update everything all the time. Or, So there are various approximation algorithms. As you can see, these things also tend to appear in machine learning conferences. So this is where I'm hoping that all these algorithms people running around in the parallel program will be able to help me come up with, I'm sure, much better things than what we have come up with for computing this metric. I said right in the outset that one didn't want to compute, one didn't want to use pure equations for reasoning, and then that was supposed to motivate the use of metrics. But how do you use a metric as a reasoning tool in any kind of logical sense? And I used to mumble about this, but Gordon Plotkin revealed the answer, which was to introduce a quantitative analog of equational reasoning. So you annotate the equation symbol with this real number epsilon, and you develop a theory of equational reasoning. So I'm not going to tell you more because I'm hoping somebody will ask me to give a talk on it. Or better still, you can ask Gordon to give a talk on it when he's here. Radu Mardare will be talking about this at the upcoming uncertainty workshop. But this is something I'm quite excited about. I thought it was a naive idea when I was first listening to it. I was like, how much can you do with that? But we were able to do some things that surprised me. For example, write down a small system of equations that give you the Kantorovich metric. Simple equations, not particularly nasty ones. And small variations will give you other metrics like the total variation instead. Indeed, the Hausdorff metric is given by yet another simple equational theory written in this form. So this is, I think, starting to give us a real handle on approximate equational reasoning. This is just equational logic, and I think there's a whole world to explore with more metrized forms of logic, whatever that might mean. Finally, having gone on and on about measure theory, in the end, I must say, I think measure theory, as it is often done, is very painful. There's all this stuff about, oh, this is true on everything except a set of measures 0. This is almost surely true. This is almost surely. All these almosts may sometimes accumulate to become never. So one of the things is that why do you get results like that? It's because what you can, in some sense, really see out of measure theory is the values of integrals. And when you have things that are undefined on sets of measure 0, they don't affect integrals that you compute. That's precisely what measure 0 means. They are things that are being changed on a negligible set. So one should recast the whole subject in terms of linear transformations on the space of random variables on integrable functions. Forget measures, work with the algebra of measurable functions. So we've actually done that. We've written a long-ish paper. It's just called Approximating Markov Processes by Averaging, but in fact it includes many things. Many of the things that we did leading up to the approximation work was all redone from this dualized point of view. And there's some very appealing things there. For example, Vincent Danos, one of the co-authors, found how to express conditional expectation in a nice functorial fashion. So I think this is the this is the way I'd like to think about probability in the future. Anyway, we've come to the end of the boot camp, except for Val Tannen's guest lecture. And I must say I've been really pleased by the number of obvious opportunities there are to collaborate and interact across the disciplines. I have seen the obvious connections, of course, between Anuj's work and the stuff that Fokion defined and between other pairs as well. And even Samson and I we've been friends for a long time and have many things in common, but right now the only thing I can relate to from his last lecture is probabilistic collapse. So I think I will stop here before that happens. Questions? Answers? Okay, let's. Yep.
Can I ask one thing?
Sure.
So I mean, in the dual point of view, does all the measure 0 stuff really disappear? You never see any qualified notions?
Well, you see them. That's right, they do. So you see them in the place where you have to say stuff like, where you prove that this is equivalent to the traditional view. There's a Reitz-like theorem, and then you have to say that. Once you get past that, no, it's all gone. And it's, yeah. Doesn't mean it's all trivial, but at least that particular annoyance is gone.
Okay.
All right.
Thank you. Yes,